So our last class we derived the Planck distribution, and we also reminded ourselves that if we integrate that Planck function, this is the frequency version, over all frequencies and over all the angles in the hemisphere, so there's a cos theta that goes with the B function, then we end up with the StefanBoltzmann law. And so this is the total power over all frequencies and over the hemisphere of solid angle, and it depends on the fourth power difference between the temperatures of the object and the surroundings, the surface area of the object. There's a constant known as Stefan's constant, and then it depends on the emissivity of the object, which is its efficiency as an absorber and an emitter. So as an example, let's consider the sun, because we know the surface temperature of the sun, it's almost 6,000 Kelvin, and we know its radius, and it's a sphere, so the surface area of a sphere is 4 pi r squared, where this is the radius right here, 6.955 times 10 to the power 8 meters. It's about 100 times the radius of the Earth. Now, for the total radiant power, if we're using the StefanBoltzmann law, we need the surroundings, and the surroundings are space. And space is actually at about 3 Kelvin due to the cosmic background radiation, but we'll just take that to be about 0 because it's not going to matter very much with 5778 Kelvin. And finally, the sun and the Earth are quite good black bodies, so we'll take the emissivity to be 1. So if we just substitute in here, we'll have 1 Stefan's constant of 5.67 times 10 to the power negative 8 watts per square meter Kelvin to the 4th. Oh my goodness, okay, running out of room there, scroll up, there we are. Okay, and then that was the emissivity sigma, so we got 4 pi r squared, 6.955, 10 to the power 8 meters squared, so that square meter is going to cancel out that one. And then we need fourth power difference of temperatures. Just let me make a little extra room here. And then there we are. Didn't make a lot of room there. Okay, that's better. Okay, so now we need room for object temperature, 5778 to the power of 4, minus space temperature, which is about 0 to the 4, and that'll be Kelvin to the power of 4. With the StefanBoltzmann law, we have to use Kelvin temperatures. Of course, 273 really doesn't matter too much when you have 6,000, but, well, just the same, it should be in Kelvin. Okay, so if we punch that through and compute it with units, we notice meters squared and Kelvin to the 4th cancel out, and we end up with watts, or joules per second. And we get a rather large number, not surprising. It is the sun, after all, 3.84 times 10 to the power 26. Now, 24 powers of 10 is actually a yotta, so this is 384 times 10 to the 24, 384 yottawatts. That's the joules per second coming from the sun. Now, that energy coming from the sun is going to spread out in space over the center of a sphere, a heliocentric sphere. Now, when it gets out here to the Earth, that's an astronomical unit, or 1.5 times 10 to the 11 meters away. So that radiant power from the sun is spread out over a rather large sphere. So we had the 384 yottawatts, but that's going to spread out over a rather big sphere, 4 pi r squared. And because, well, one astronomical unit is so large, even though there's a lot of power, by the time we reach the Earth, we're down to about 1,400 watts for every square meter of area at the Earth's orbit. So if you took a 1 meter squared surface out there, you'd get 1,400 watts of solar energy impinging on it. That's over the entire frequency spectrum. So all frequencies at that point, the total would be 1,400 watts. Now, the Earth, being a sphere, is going to intercept a portion of that, right? The Earth is actually a tiny little dot on this huge heliocentric sphere. Look at the area of that heliocentric sphere. It's really large. The Earth, if we imagine the solar radiation coming in and striking the Earth sort of makes a circular shadow there. So we're intercepting an amount pi r squared, where r is the radius of the Earth, right, which is 6,380 kilometers, or 6.38 times 10 to the 6 meters. And so we can look back to our ratio. Intensity is power over area, so power is intensity times area. And the area in question is the cross-sectional area of the Earth. Which is pi r squared. So here was the solar intensity, the 384 watt-watts divided by 4 pi times 1 astronomical unit squared, and we calculated this ratio to be 1400. Then we multiply by pi r squared, where r is the radius of the Earth. So here, this part here, that we worked out above is 1400 watts per square meter, and then we multiply by pi little r squared, where that's the radius of the Earth, 6.38 times 10 to the 6 meters. And so here we get 1.81 times 10 to the power 17. Meters squared cancels out. This is watts. Since a peta is 10 to the 15, this is 181 petawatts. So there's 181 times 10 to the 15 joules of solar energy striking the Earth each second. That's sort of like the Earth's energy budget. Now that is, we say, at the top of the atmosphere, way up here. The atmosphere, of course, affects the amount of energy that we receive down on Earth because there's reflection, and that is going to reduce that 1400 watts by a factor of about 30%. So there's about 28.6% of that 1400 watts per square meter that doesn't reach the Earth. So we actually only receive, what is that, 71.4% of that 1400 watts per every square meter. So what are the atmospheric effects? Well, it's reflection and absorption. The atmosphere, of course, also convects energy around, and it distributes it over the hemisphere, and even over the backside of the hemisphere. Atmospheric convection keeps the dark side of the Earth from freezing at night. At least at certain latitudes it does. So 71.4% actually reaches the Earth, makes it through the atmosphere. And so we're down to about 1,000 watts per square meter. So that's about the maximum you would ever find on a summer's day, even, say, at the equator, where the sun would be directly overhead. So, of course, this will vary over the day, and it will also vary with weather conditions. Clouds and things like that increase the reflection and reduce the amount that's received at the Earth. And so the solar potential, which is averaged over the whole year and all atmospheric effects, including weather, and even over, darkness. So this is a 24,365, so it includes the fact that you only get sun for a certain number of hours a day. In Canada, we're down to about 1,000 watts per every square meter. So if you have a 1 meter squared solar panel, you're getting an input solar energy about 100 watts, averaged over the whole year. Other places do better than that. The optimal place seems to be around the tropics. There's a good balance of having sunny days and getting nice direct sun. So a place like Phoenix is a really good place to have a solar panel. If we plot graphs of, say, the solar intensity in Vancouver and in Phoenix, it would look sort of like this. So this is PW, which is Phoenix's winter, okay? Oh, there we go. And so, it around noon is the maximum intensity, and it drops off later in the day. And in the morning, as the sun comes up, the solar intensity will peak. And then, in the summer, obviously, with the tilt of the Earth's axis, you're getting more intense sun at the middle of the day. Get rid of these labels. But, it's still the same basic shape as Phoenix in the winter. Okay, so there's solar intensity graphs in Phoenix in the winter and the summer. How about Vancouver? Well, Vancouver, our sunlight is much less intense than Phoenix's is in the winter, and we have a shorter day. But in the summer, our sun is pretty well as intense as Phoenix's is, and we actually have a longer day. So there's a lot more day variation for us than there would be for points further south. I mean, if you get at the equator, they don't get those longer days in the summer. And so in the summertime, you're going to get more energy from, say, a solar panel than you would in the wintertime in Vancouver, and it becomes, appreciable. And so you can see there's a length of day effect there, and we can understand that if we sort of look at a picture of the Earth here. So here's the Earth, and here's a cylinder of sunlight coming from the sun and passing through the atmosphere and reaching the surface of the Earth. So there's a couple of things we can get from this. First of all, if we imagine that this is the North Pole, and so we're looking down on the surface of the Earth. Put the North Pole up here. That's what I'm trying to say. That's what I'm saying up here. So north is up here. So Vancouver's here at about 49 degrees, and then Phoenix is here down at, I don't know, maybe 15 degrees or something like that. In the higher latitudes, the sunlight has to pass through more atmosphere, okay? And then it also gets spread out over more area. Whereas down here, sort of in the tropics, the sunlight is passing through less atmosphere. B prime is less than this distance B up here, okay? And then it's less spread out because the sun is more overhead. So the area A prime is less than the area A up here. So this means you have more intense sunlight, when the sun's directly overhead. So there's more intense sunlight at the tropics than there is here in Vancouver. We can also use these diagrams to explain, say, the time of day effect. Whereas if we imagine that the North Pole was here and we're looking down from above, if this is Vancouver, this is like sunrise. So we're just coming into the sun. That cone of sunlight early in the morning, first of all, it's passing through more atmosphere. Second of all, it's more spread out over the surface. And so then, now Vancouver is swung around, and so this might be a day in the summer, and the sunlight is now directly overhead. It's passing through less atmosphere, and it's less spread out over the surface. So it's most intense here at around lunchtime. So these two pictures sort of explain some of the effects that we see. First of all, with latitude, and then second of all, with time of day, right? The general increase in intensity over the length of day. All right, so these calculations that we've just done, we use the StefanBoltzmann Law to calculate the Earth's energy budget. And we use the albedo of the Earth, which was that 30% value, to calculate the amount of solar intensity that's actually hitting the surface. So on a summer day, it's about 1,000. Averaged over the entire year in Canada, it's about 100.